Yeah, good morning, ladies and gentlemen, and thanks very much, Dr. Susanna, for the invitation to speak and also for the kind introduction. So, yes, my presentation today is excuse me, based on a paper I wrote for this year's Oslo Land Conference, entitled A Simple Recipe Guide to Gravity Concentration. And I must admit, when I started writing the paper, I did envisage it would literally be a simple: take the 3 tonnes of reground middlings you produced earlier, add some water and run them over the Wilkley tables, and voila, you've got recovery. But since I've become a consultant, I've realised it's definitely worth transforming anything simple and elegant into a confusing mess that only I can understand. So I'll run excuse me, I'll run through the presentation in the following order. I'll give a bit of a background on when gravity ruled the Earth, some gravity processing on how it was practiced in gold roughly 30 years ago and now. I'll introduce some gravity processing concepts in an effort to simplify the topic, and I'll move on to the excuse me, the gravity recipe. Now I want to talk about a summary, or give a summary of the Renison Tailings retreatment case study, which was a fairly interesting one, and I'll finish off with some gravity paradigms. So to start off, a photo there of the wrecked mountains of Las Medulas in Spain, and the Romans extracted 6.5 tonnes of gold per year on riffles for over 250 years from that site. And until flotation and magnetic separation and other processes came along, gravity really was the only large-scale mineral concentrating process available. And when there's only one process and it's been around for a long time, it's fairly certain the principles are going to be well understood. And when I wrote the paper, certainly I was suggesting there's been a loss of gravity processing knowledge, particularly due to the influence of flotation and other technology advancements, but also in gold processing as well. So some holiday photos here, and this is a photo I took looking up the endless stairs of the ghost town of Sul, which was built for El Teniente workforce in Chile, and it's from about 1911. And El Teniente, which is still the largest base metals underground mine in the world, started with gravity processing. But they're getting very poor copper recoveries of around 50%. The ore slimed easily. It was lost on the vanners, which meant that it was ripe for being replaced by flotation, which lifted recovery to up to 90%, which is a step change if there ever was one. So while still on holidays and also still on copper, probably one of the last stands for gravity in copper sulfide processing was at Kennecott in Alaska, where they use gravity to separate massive chalcocite from the limestone host using jigs and tables. And the problem for gravity was that flotation could efficiently extend itself down to particle sizes gravity can't hope to match. So when they started treating the gravity plant tailings through flotation, it lifted recovery, and that sounded the death knell for gravity in treatment of sulfides, particularly as they become finer grained over time. But gravity has managed to hang on in gold and metal oxides. So some gold processing then, and this is the block diagram from the first gravity circuit I worked on in the 1980s at Warrego in the Northern Territory, and all those orange boxes represent a gravity process. And making a final product that was suitable for smelting on site to a doré, particularly in the presence of sulfide minerals, took a lot of gravity unit processes, which made for a complex flow sheet. And some of the common bits of equipment that you're dealing with, such as spirals, the tables, and back then Reichardt cones, They make three products. They make concentrate and tailings, but they also make middlings. And middlings are always a major issue. And it's anyone who spent time in gold rooms in the olden days will tell you that the final steps to making something you could smelt was very, very time and labour consuming. And it was usually a bit nasty using mercury amalgamation or calcining or strong acid digestion. And because of the time and the labour intensity and the hazard to health, in the 1980s people with gold gravity circuits started to look for options for hydrometallurgical treatment of their gravity concentrates using cyanide. So this is a block diagram for a more recent gravity circuit that was a bit easier to work on, and this was at in the Northern Territory as well, at Union Reefs. It's a very simple flow sheet, and it's only got one gravity device, and just about every gold plant on the planet has this sort of arrangement now. And notably, the final gravity product from these high G-force gravity concentrators is basically middlings. So when you combine that with the intensive cyanide leaching on this site through the Acacia reactor, which incidentally was developed at Union Reefs, the gravity process has marched a long way back up towards the recovery end of the grade recovery curve. Base metals, and this is the block diagram from the Renison belt. Tin concentrator I spent a lot of years working on, and it wasn't a very pleasurable environment a lot of the time. There are no hydrometallurgical magic bullets to treat the middlings here. The gravity flow sheet is necessarily complex and requires good feed preparation for each stage of gravity concentration. And in gravity, middlings are always the challenge, and they become more and more challenging the finer the particle size gets. And without wanting to frighten anybody, I thought I'd throw up the actual Renison belt flow sheet, which was at the start of operations in 2008. And believe it or not, this was after a lot of work was done to try and simplify it. So some gravity processing theory in fairly ignorant terms. So as a physical process, obviously gravity has a whole branch of science supporting it, i.e. physics. But the practical question should always ask is, can I use gravity processing to concentrate my mineral? And the concentration criterion is described in detail in a lot of the old textbooks and maybe a familiar concept to any old gravity practitioners out there. And I must say that the ratio of heavy and light mineral SGs, that does give you an indication of the amenability of your suite of rocks to gravity processing. So what it says is for coarse particles a concentration criterion over 1.2, and for fine particles over roughly 3, say gravity's a goer. And I've used a pure mineral example for gold and pyrite here, which indicates you're going to have absolutely no problems separating gold from a pyrite host. But, and there's always a but, excuse me, what happens if the gold and pyrite particles are a different size and shape? So unfortunately the concentration criterion is not a definitive go or no-go for gravity. Size, shape and texture of the particles is critical, and it's rarely discussed in the textbooks but in any detail, but the way the particles interact is very important. It's generally very specific to the type of equipment that's being used. And anyone who's ever tried to separate big flat plated gold particles from coarse material in a gold room will certainly attest to the annoying influence of shape. So the first simplifying concept I want to introduce is if all the particles are the same size and shape, then you can get pretty much a perfect separation. And the example for this actually exists in the real world, and grain cleaning, wheat cleaning, or closer to home, CIP carbon cleaning. All those particles are the same size, so if you use very tight classification before your air tabling gravity process, you can get a virtual perfect separation. But unfortunately in mineral processing, virtually any scale, there's invariably going to be a wide size range a wide particle size range after comminution, and commonly there's going to be a wide mineral SG range, and both of those make gravity separation inefficient. So the next simplifying concept I want to introduce is apparent specific gravity. And what this means is that large and medium or even light SG particles will often behave in the same way as small and high SG particles in a gravity concentrator. So a simple way of thinking about this is that both particles have a similar apparent SG. And some rough geometry tells us that if they've got the same shape, a 50 micron gold particle has the same mass as a 75 micron pyrite particle, or even a 95 micron quartz particle. And often these exist after comminution. So in the hustle and bustle of processing, a gravity concentrator can really struggle to see these particles as different. And cyclones, include cyclones as in that gravity concentrator group. So there really are no shortcuts in gravity processing, and like all processes, it works best in a logical sequence. And we generally know what those are: liberate, reject the competing minerals, classify to decrease the size range, and go through gravity processing before going around again with the millings and the tailings. But it's quite common to observe that steps in gravity processes will be missed, or the consequences of actions taken are not well understood. An example we see very commonly is people will open the aperture on a screen before a Nelson or a Falcon in a gold plant, and they're trying to get more feed into it to increase the recovery. And that might actually have the opposite effect, because what they're doing is letting in lots of particles with a similar apparent SG, and they crowd out the valuables. And this leads me on to the most important concept in gravity, and that is eliminate the competition before gravity processing. And we're all familiar with the puzzle of the farmer trying to get his bag of wheat and his chook across the river, and he's always got something inappropriate like a wolf or a fox in the mix. But in this case, you definitely don't want the fox getting into the SS gravity. So even though he's off to a good start there, if he really understands gravity processing, he'll make it certainly the outcome. So on to the ingredients. Ingredient one is characterising the material you want to treat, and regardless of the process, this is always a good place to start, as we all know. And the geology can tell you a lot about whether gravity processing is likely to be successful. And I've used low sulfidation epithermal gold deposits as an example here. These are formed at shallow depths, at low temperatures, in contact with groundwater. So in my ignorant geology thinking, I think it's likely to have frozen fairly quickly. So they almost invariably, and I'm yet to see a major outlier on this, they almost invariably have gold as less than 50 micron particles, and they in the presence of sulfide minerals. So if you're thinking about gravity processing only to produce dorate, it's going to be very challenging. And often we'll go to a site and they're having problems with their gravity, but you talk to the geologists and they've never even seen what it is they're after. So it's a really good idea to find out whether the content of the mineral in a size suitable for gravity recovery is statistically significant. And there are many methods available these days. I'm not going to go through them to measure how your mineral occurs and give you an understanding of the mineralogy of the material, the mineral associations, the particle sizes and the liberation characteristics. And I've always thought the photomicrograph is a very powerful communication tool. However, I included a photo in the bottom right there of that big lump of gold, and that was in the tailings from a 55,000 tonne per day copper concentrator. And I'll put it there for a cautionary reason. That's the only one we ever saw like that. And as one swallow doesn't make a summer, one bit of 75 micron gold certainly shouldn't make a gold ring. So on to ingredient 2, and that's planning the process. And this is because gravity processing needs a definite set series of steps to work efficiently. So before starting off with any test work, a lot of thought should go in as to how to get the feed into a form that gives it the best chance to succeed once it's presented to a gravity device. So ask, what are the competing minerals in a gravity process, and not just on the basis of SG, but also on hardness, because as large and light particles often behave in the same way as fine and heavy particles in gravity. They have the same apparent specific gravity. If the light minerals are a lot harder, then you're actually creating a lot more competition for your desired mineral in the comminution and classification step, particularly if you're using cyclones. And often there's a perception that, particularly in gold, that it's the gold you're concentrating in a gravity device, whereas if the gold is locked with pyrite, and the gravity process, then the gravity process is actually concentrated to pyrite, and the gold is just along as a passenger. And a sulphide mineral specific process such as flotation might be a lot more effective at recovering the gold. So gravity success is really all about feed preparation. So it's preferable to classify if you can with screens, but regardless, get the size range as tight as possible and use whatever processes are available, such as flotation or magnetic separation, to stop the competing minerals getting into the gravity device, because once they're in there, they'll beat up your valued mineral and they'll win. Ingredient 3 is testing. I just wanted to give a bit of a summary on, or a bit of a précis on testing, and it should definitely be restrained until you understand your ore and the process is planned as to how you're going to do it. And a commonly observed failure is that people will run a gravity test and it's just an upfront catch-all, and it doesn't in any way mimic the process conditions, and in particular gives a mass recovery orders of magnitude higher than is possible in the plant. Or worse, they make a very rough product and they equate the recovery achieved with a much higher grade product further down the grade recovery curve. In labs, a lot of gear used in the olden days had a load of variables, and as such could be highly operator dependent. Super panners are a prime example. I remember being trained on a super panner and being horrified at the sheer number of things I could play with. But even simple tables in a lab can have different stroke lengths and frequencies and slope and lean angles, and so unless you're getting the same person doing the test, you can get differing results. I must put a plug in for the little Falcon and Nelson lab units these days. They're a lot simpler, a lot less variables, and they have improved standardisation. For example, Andre Laplante's gravity recoverable gold test. And it's rare to see, but a knowledgeable lab will also assay for other things, as I alluded to before, to give information on what the process is doing. For example, if the recovery of sulphur is the same or higher than the recovery of gold, then the gold is just likely along as a passenger, and the gravity process is actually recovering the sulphides. I've got a couple of horror stories from labs, and probably the worst one, not this one up here, but the worst the worst test and results interpretation we've seen from a lab was where they took the whole test feed sample and mixed it with mercury, and then took the residue of that and then did their standard flotation tests. And the gold that ended up in the amalgam was stated in the laboratory final report right up front in the summary section as being the gravity recoverable gold. And a plant worth 7 figures was actually designed and built with the expectation that they're going to get 50 or 60% of the gold in the gravity circuit. This one I've got up here is actually it's a more common example to look out for, and this actually came from a very reputable lab who recovered 6 or 7% of the feed mass into the concentrate, and then happily stated in the report that the resultant 40 to 60% gravity gold recovery was a very good response. In real life, tragically, the Falcon concentrator they had on site could only recover about 0.03% of the feed mass, which resulted in a lot less gold recovered, and initiation of the well-known law of diminishing metallurgist problem comfort.
So was that because they made an amalgam?
Yeah, and said it was gravity. Yeah. So the influence of good feed preparation on gravity success becomes very apparent in ingredient 3 testing. For example, if a preceding flotation step is required to get rid of all your competing sulfides, the following gravity step will just fail if the flotation step hasn't done its job properly. So each test is about getting the result that allows the whole process to work. And I would strongly suggest that gravity is particularly sensitive to feed quality. For example, if you're doing a rougher flotation test and you didn't quite achieve the mineral liberation you're after, the poorer quality composites can still be recovered. But if you're doing a gravity test, they'll end up in tailings or at best middlings. And no one seems to get too excited when you talk about optimising flotation tests, where everything from the source of the water to the grinding media and the chemical conditions are considered by a competent lab. But it's quite common to see a bad gravity test result taken as gospel, even though the poor thing was fed with a lot of rubbish. So the last part of ingredient 3, testing, is interpreting the results, and we've already shown what can happen if the laboratory or the design engineers don't recognise that 0.03% mass recovery to a concentrate is unlikely to give you the same recovery as a 6 or 7% mass recovery does. And John Glenn, who's down at Burnie, is a great gravity practitioner, and he certainly gave me a lot of help for this paper and earlier. And he'd be annoyed if I didn't give a plug for interpreting the results to be meaningful information for a liberation condition using techniques such as Dell's release analysis, which I've got an example of up there. And that was developed for flotation, but it equally applies to gravity. And even size-by-size analysis of concentrates, middlings and tailings is useful. It's a relatively simple way of finding out where your minerals have gone, and if you can assay directly for some part of your mineral, you can figure out what size fraction it's gone into. So onto a bit of a case study, and this was a fairly tough gravity job. Renison Bell, it's in Western Tasmania. The tailings dams now contain over 24 million tonnes of material at 0.44% tin and half that of copper. After the start of the plant in the late 60s, they had a lot lower than expected recovery. And that prompted a search for ways, well, firstly for improving and secondly retreating the tails, and they always met with limited success. And the main reason for that is the cassiterite in the tailings is typically very fine and well below the normal size range where you consider gravity processing a good idea. Plus the mineralogy includes a whole lot of sulphide and oxide minerals of medium to heavy SG. It's all dominated by pyrrhotite. So we had a major rethink in early 2006. There was a particularly poor set of results from some fairly standard gravity test work, and that had got nowhere near our stretch target of over 50% tin recovery into a 10% tin product, which we considered suitable for downstream pyrometallurgical tin fuming. So really doing the same things again that have been tried since 1972. It's a first-class example of idiocy. You know, we really had to do something different. And happily at that time, an opportunity to try an ultrafine Falcon lab unit came up. And so the first test was literally go down the back with a scoop and grab a sample of some slime tailings, which had a cassiterite 80% passing size of just 12 microns. And we got an amazing result. You know, we got roughly 90% tin recovery into just 25% of the mass. But we didn't actually even tell anybody because we knew what had happened if we did. We didn't, before getting overexcited and charging off and throwing the kitchen sink into it, we decided to draw breath and do a detailed characterisation study on it. Because we really had to know the occurrence of the cassiterite to have the best chance of maximising recovery into something we could fume. So there'd been a lot of work done. So we undertook a detailed review of the mineralogy and data to see how big the cassiterite was, what minerals it was associated with, and the general mineralogy of the tailings to find out what the likely troublemakers were going to be. So once we had a good understanding of the characteristics and the mineralogy, we set about planning the process. And the liberation data gave us a target grind size, which I think was about 53 microns. But then we grouped the minerals as sulfides or oxides, and then within an SG range. The objective was to form groups of minerals that could be expected to behave similarly in any part of the process. So we had the Group A sulfides, which are all pretty heavy. I think the heaviest was arsenopyrite, or at least medium SG. Had the light oxides with an SG below 3.2 in Group B, Group C oxides with a medium SG, and we gave cassiterite its own group because it was special, and Group D. The list there. So fundamentally, the process plan was a bit like the whack-a-mole arcade game. You just smack everything that sticks its head up that's not cassiterite. So the first step is to get the cassiterite liberated, and then use flotation to get rid of the main competition, and that was the Group A sulfides. We then used the ultrafine Falcon to effectively de-slime the material and get rid of the Group B low SG oxides. And there's always been a wicket-keeping sulfide scavenging stage required at Renison, and it's mainly been used to get rid of any remaining Group A very fine and slow-floating sulfides, in particular arsenopyrite. And finally, after all that, tin flotation, which was to get rid of the Group C medium SG oxides such as siderite and tourmaline, and any coarse hard silicates that were recovered, like quartz that were recovered in gravity. And hopefully we'd be left with D, the cassiterite. So no matter what results we got from the early tests, and some of them were pretty average, we just didn't deviate from the test plan. And every process stage test was practiced to get the equipment and the conditions right, and then developed and optimised on variability samples. So there was always constant changing that we could track. It took about 3 to 6 months, I can't remember exactly, and there was a particular focus on the sulfide flotation because that gets rid of most of the mass, and also the ultrafine gravity because it was a fairly novel thing at the time, and we weren't too sure about scale-up. But after our efforts, we eventually cracked over 55% tin recovery into a nearly 10% tin concentrate. And all our further efforts after that just improved the results before we conducted a full and extremely painful process pilot plant to make enough concentrate for ultimately successful fuming trials. So, onto the paradigms. A lack of gravity knowledge and the quest for recovery will create the middlings conundrum. And middlings have a bad habit of building up in any circuits, as we know, but often gravity equipment has no way of relieving that build-up until there's such a mass of it in the feed, it'll just vomit itself out of the circuit, usually the tailings. So the process design should consider how they'll not be introduced into the process in the first place. And if they do happen to get in, where they're going to be sent for retreatment before coming back around as suitable to either go to final concentrate or tailings products. And if you're running a gold gravity circuit like a lot of people are these days, in the presence of lots of competing minerals and sulphides in particular, if you've got intensive cyanide leaching in your toolbox, then making a low-grade middlings at a high recovery is fine. But if you can't use intensive cyanide leaching on your site, or for whatever reason, you're going to go back in time, and you're going to have to expend a lot of really hard work converting those middlings and those low-grade products into a smeltable concentrate and maintain a high recovery. Number 2. Each gravity unit process should be given one task only to perform, either grade or recovery, but not both. And again, the high G-force concentrators are a good example in gold and base metals. They're there for recovery. And grade and recovery really can only be achieved in one step if you've got a very coarse liberation size, there's a very narrow size range, and there are no competing minerals. We already talked about grain planning, but I spent quite some time at Hill End, which is north of Bathurst in New South Wales. We're close to where gold was first discovered in Australia, and all the gold there was in plus half millimetre particles. It was huge, and yet we still couldn't achieve grade and recovery in one gravity step. So it's not a very common situation. Number 3, grind tailings, not concentrates. We had to sort of give a bit of thought as to why you do this when I was writing the paper. And it's unlike magnetic separation or flotation, where you can make a really rough concentrate at a high recovery before you regrind to provide that liberation for final cleaning. Gravity processing will separate the liberated minerals in the feed, and the composite particles will report to middlings or tailings. And the reason for the difference is that magnetic separation will, flotation can, but gravity processing cannot recover poor quality composites. Number 4, avoid over-grinding. We know this doesn't apply just to gravity processing, but gravity processing becomes a lot more challenging at fine particle sizes. So in comminution circuits, you've really got to provide an exit point for the liberated high SG minerals before they become so fine that either gravity separation becomes impossible, or you've got to apply some horribly expensive process to get them out. And number 5, reject the grinding media and any other competitors you've added. And if you're dealing in grams a tonne and you're throwing in kilograms a tonne of steel, you're adding a lot of competition. Admittedly, this is not generally done commonly these days, and it's a bit pointless and difficult in high capacity gold gravity circuits using high G-force concentrating devices. But in the old days, it was quite common to see a magnet over strakes and tables to avoid recovering the steel into final gravity concentrates prior to smelting. And do have an example of this at Renison where we had a magnet on the final concentrate, and which actually gave us a significant grade uplift of 3 or 4% tin. And that was simply just by getting rid of the steel load in the gravity circuit. So, yeah, I've pretty much got to the end now, but you know, I wanted to give a final message that you could take home that you'll hopefully remember, and that is, if you do nothing else in gravity, just ruthlessly eliminate the competition. Thank you.